Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about instruments that can help us measure pressure. And there's two different types of pressures that we like to measure in chemistry. One of them is going to be atmospheric pressure, or the pressure in the classroom. And for that, we're going to use a barometer. And then the other type of gas pressure we like to measure is if we collect some type of gas in the classroom or in the laboratory, we want to measure the pressure of that gas. And for that reason, we would use a manometer. Okay, so barometers measure atmospheric pressure, and manometers measures gas that we collect in a lab setting. So let's start talking off about the barometer. Okay, the barometer is going to measure the atmospheric pressure or the pressure in the classroom. And the way it works is that we have this pool of mercury. Okay, and as the gas pressure increases, there's going to be more gas molecules pushing down on that pool of mercury. And as it pushes down on that pool of mercury, it pushes mercury up this tube that has been filled with mercury. And the level difference between the level of the mercury pool and the level of the mercury that's inside the tube is actually the pressure of the room, or the atmospheric pressure in that room. Okay, so if this pressure once again starts to increase, it pushes down on the pool, which would then push mercury up. Okay, and if the pressure ever reduces in the classroom, like let's say there's less pressure, then some of the mercury would come out. Okay, and the pressure of the room is always the difference between the meniscus level in the tube and the meniscus level of the pool of mercury. And let's just say that we measure that, and we're going to measure that in millimeters of mercury, and we measure it out to be, let's say this height difference ends up being 749 millimeters of mercury. I want to remind you that there's a conversion factor between millimeters of mercury and torr, and that's a 1-to-1 ratio. So if we have 749 millimeters of mercury, that is also equal to 749 torr. Those pressure units are exactly the same. Okay. Now, to convert torr or millimeters of mercury into atmospheres, which tends to be the unit that we like to use in chemistry, we use a conversion factor of 760 to 1. So I'm going to take this 749 millimeters of mercury, and I'm going to convert it from millimeters of mercury or torr into ATM. And for every 1 ATM, there's 760 millimeters of mercury or 760 torr. So if we do that in our calculator, this pressure is going to come out to be 0.986 ATMs, or atmospheres of pressure. Okay, so we're going to pretend that this barometer is sitting in the classroom with all these other manometers. Okay, so the atmospheric pressure all throughout the classroom, okay, is going to be this 0.986 atmospheres of pressure. Okay, so then we get into our first manometer. Okay, and manometers can come in two different fashions. Okay, they can have like a cork, or it's sealed off at the very end, and we call those closed-ended manometers. Okay, or they can be opened like all the rest here. Okay, and they're open to the atmosphere. Now, if they're open to the atmosphere, we got to consider the atmospheric pressure. Now, I'm going to explain that when we get to them. Okay, but if it's sealed off, we really don't have to worry about it. Okay, so the way this works is if there's a gas that's inserted, and sometimes that's inserted with some type of syringe, okay, that's plunged in there, and then that gas is going to expand, okay, and then it's going to start pushing down right here, just like the gas molecules over here push down, and that's going to create a level difference, okay, in the meniscus of the mercury, okay, and let's say that this meniscus level change is 30 millimeters of mercury. Remember, millimeters of mercury and torr are the same thing, so that would be 30 torr as well. And of course, if we converted that torr or millimeters of mercury into ATMs, we're going to set it up the same way. So 30 millimeters of mercury to ATM is 1 for every 760 millimeters of mercury. And if we work this out, it comes out to be 0.039 ATM So I'm just going to write that down there because we're going to use this number quite a bit. So 30 millimeters of mercury is the same thing as 0.039 atm. So the pressure in here would be 0.039 atm, and that's how much it's pushing. The more gas molecules that would be in there, the more millimeters of mercury we would have, and the more atms we would have. So this is a way that we can measure pressure of a gas in a laboratory setting with a closed-ended manometer. Okay. Now, if it's open-ended, we have to take into account the atmospheric pressure, because this gas molecule, it's expanding, right? And it's pushing down right here. But remember, we have atmospheric pressure out here. And if this is open-ended, it's going in there too. And it's going to push down as well. And I have an example here of a U tube. Okay. It's just a tube in the shape of the U. And both sides are open, and they're both receiving the same pressure. So you can see that the meniscus level is exactly the same. Okay. So if we have a gas in here, okay, and it pushes down on the meniscus level on this side, but the atmosphere is also pushing down the same exact amount, well, then what that means is that the pressure of the gas that's inside here is equal to the atmospheric pressure, because if the levels are the same, not one is stronger than the other. Okay, so the pressure of the gas is equal to the atmospheric pressure. Well, what is the atmospheric pressure? We have to come back to our barometer. The barometer tells us the pressure in the classroom is 0.986 atms. So if the atmospheric pressure is 0.986 atms and the levels are the same, well, then the pressure of the gas would be exactly the same in this type of situation where the meniscus is exactly the same. Okay. Well, what if we have an open-ended manometer where the values are not the same? Let's say this gas here, okay, looks like it's pushing down more than what the atmospheric pressure is pushing down, and there's a level difference. Okay. Well, if this side is pushing down more, if the gas is pushing down more, then it's stronger than the atmospheric pressure. So we write the equation like this. The pressure of the gas inside here is equal to the pressure of the atmosphere plus the difference in the meniscus level. So remember, our atmospheric pressure is 0.986 atms. Okay. And if we wanted the pressure of this gas, we would measure this height difference. Okay. And if this height difference came out to 30 millimeters of mercury, well, remember, 30 millimeters of mercury is equal to 0.039 atm. Well, we would just put that in here, 0.039 atm. So this gas pressure would be equal to the atmospheric pressure plus this extra 0.039 atms. And if you add those two numbers together, you get a pressure of 1.025 atm. And I just have like a little demonstration to kind of show this. Okay, so right here, the gas pressure on both sides is exactly the same, okay, because that meniscus level is the same. And what I'm going to do is I'm going to try to put this blunt plunger in and push some gas in there so the pressure will increase, and take a look at what happens to the meniscus level. Now let me try that again, okay. Probably didn't seal it off really well, but kind of, it's not sealed off perfectly, but you could see that that meniscus level, when I pushed down the plunger, it was pushing the meniscus level because the pressure of the gas on that side was actually stronger than the atmospheric pressure. But since it wasn't sealed, it kind of went back to being level on both sides because it wasn't perfectly sealed. So kind of like an okay demonstration, okay? We come over here to this last one, okay? And which side looks stronger? Does the gas side look stronger, or does the atmospheric side look stronger? Well, it looks like we're getting more of a push out here from the atmosphere than what is happening with the gas, because it's pushing down on the right-hand side more than it is on the left-hand side where the gas is. So in this case, the atmospheric pressure is stronger. It's equal to the pressure of the gas plus the pressure of the height difference because the atmospheric is equal to the combination of the other two. Now, if I wanted to get the pressure of the gas, what I would do is I would subtract on both sides. So the pressure of the gas is equal to the pressure of the atmospheric pressure minus this height difference. And this height difference, we'll just keep apples to apples. We'll keep saying it's 30 millimeters of mercury, which is equal to 0.039 atms. So this gas pressure is equal to the atmospheric pressure, which is 0.986 atms, minus the difference in the height, which is 0.039 atms. That is equal to the pressure of the gas. So the pressure of the gas, 0.986 minus a 0.039, gives me a number of 0.947 atms, because this gas pressure is not as strong as this outside. So if this outside's 0.986, inside here is only 0.947, and that's why you see a more of a push on this side, on the right-hand side, where the atmospheric pressure is, than the gas side. So I hope this helped you understand how barometers work with the atmospheric pressure, as well as manometers that either close-ended or all these different scenarios that you can have for open-ended, levels the same, gas pushing more, atmosphere pushing more. And if this helped you, please give it a like, a subscribe, even leaving a comment will really push this YouTube algorithm to push this stuff out to other students that might be interested in learning chemistry.